Hi, this is Albert Lee doing lab for magnetic field of a bar magnet. So some introduction stuff. The goal of the lab was basically to find what happens whenever you take a magnet, place it at one place, and then get a magnetometer and measure all the different magnetic fields at different points. So then after that, we simulate a magnetic field using some glow script, and then we're gonna compare the two and see how they differ. Some things you're gonna need to know for the lab are the Biot-Savart laws. So this is just saying how you find a magnetic field from a known observation point and distance from source. So you can see that basic, for any difference in length equation right there. And then right below that is for a loop. Right below that is for the dipole. And then in the dipole one, you're gonna have to use mu. Mu is actually the magnetic dipole moment, which is calculated as I pi r squared, which if you look at that a little more closely, that's just I times the area of whatever the source is. So some more useful equations are this, well, especially for this lab, are this right here for a perpendicular dipole versus a on axis. Seems that on axis is just two times what perpendicular is. And then you have this bottom one, which is just the general magnetic field equation that we're going to use in glow script. Some assumptions you're going to have to make is that the magnet is uniform uh, and perfect, I guess, slash ideal to make it a perfect magnetic field. And then the magnetometer is ideal, perfect working one. Some preliminary findings we got is that the magnitude of magnetic field is inverse of distance. So basically what it's saying is that further you get from the distance, the lower the field is. Closer you get to the source, the bigger the field is. So then dipole moment is right there. The experimental magnitude or experimental vector is right there. And then the simulated one is on the bottom. So here's a procedure one, the first one we did. You see on the left the diagram of what the magnet actually looked like, and then you just put your phone to the right of it. You can see at the bottom right is a picture we took from doing that lab. You can see it's maybe like 9 centimeters away. So here it is. Here are the instructions for that. Specifically, you basically just read it at each of those intervals listed at 4A. Part two, we're basically getting off axis, so we're trying to see what it is when it's not in line with the magnet. Then here are some results we got. So you can see at the top that it is an inverse relationship. As it gets closer to the magnet, it gets stronger. The magnitude of the magnetic field gets stronger. And then, of course, inverse, further away is weaker. So looking at the results in math, we get the slope of that graph you saw is using that equation. We solved for k using Euler's constant. Find krn from these two equations, or you find that kr to the n is equal to that. And then, to find the magnetic field in the y direction, all we did was subtract Earth's natural y off axis. So basically what we found is when the once again, when the magnetometer is far, it measures close to zero magnetic field in the x direction. And then when I can't say this word, magnetometer is closer, produces a larger magnetic field. Here's a dipole, or the glow script we got. There's my equation at the top left to make a dipole. At the bottom, you can see all the distances and observation points we changed up. Then this glow script is also changing up basically observation points and arrows. And then at the bottom right, we're making the magnetic fields from the arrows. And this is what we got for a simulated model. Here's the mathematic analysis. You can see our magnitudes of the magnetic fields, and it's 173% difference for the simulated magnitude. So big difference. Errors, a lot of errors could have happened. Several other sources of magnetic fields were in the room at the same time. Incorrect labeling of the magnetometer on the phone. App glitch, it was looking a little weird. A lot of stuff happened. So Yeah. Well, some final thoughts though. What if you oriented your experiment to compensate for magnetic north? How would it basically change? Well, if we didn't do that, it would be pretty bad because the X direction would affect it from the Earth, and it would affect the Y. However, it wouldn't affect the Z because we were parallel with Earth. Now, what if we stuck two identical magnets together end to end and run the experiment again? It would just double because of superposition. So yeah, it would increase double and decrease the measurements.